In World War II in Europe, a key to victory was strategic bombing of German industrial sites. In the early part of the war, that process wasn't going well. Losses of bombers were excessively high. One of the reasons why was the lack of an escort fighter that could fly with the bombers and protect them all the way to the target and all the way back. Now, the solution to that problem was this. This is the P-51 Mustang. Behind me, this is a North American aviation-built airframe mated with a British-designed Merlin engine, in this case mass-produced by Packard. Now, the Packard Merlin was the key to the performance of the P-51, and mass production of the Packard to American standards, using American mass production methods, in fact, allowed this engine and this aircraft, in turn, to be made in numbers sufficient to actually overcome the tide of the German Luftwaffe. I'm here in Raleigh-Durham, North Carolina, and I'm standing in front of Rob Connolly's immaculate P-51 for a reason. That Packard Merlin engine I just discussed, well, an exhaust stack cracking problem caused a need for a replacement part. Now, John Murray, president of Concept Laser Inc., a friend of Rob Connolly's, well, they discussed a way of using 21st century technology to create replacement parts for this 70-year-old aircraft. So I spoke to John Murray and Rob Connolly about the project. I'm with John Murray. He's president of Concept Laser Inc. out of Grapevine, Texas. And John, the Packard Merlin engine I discussed, the enabling technology that made the P-51 the remarkable aircraft that it was. Now, you're a pilot yourself at this point. I understand that you've evolved a 21st century 3D printing technology to make replacement parts for this 70-year-old engine.
Right, it's very interesting. The 3D printing process, I was talking with Rob Connolly, who acquired this aircraft, which is a real icon in the P-51 Mustang world. We were talking about ways, how do we leverage this technology, not only for today and like GE's doing, they've just purchased Concept Laser and they're doing exciting things with fuel nozzles in the future. And we thought, well, we're going to reach back in the past, over 70 years on an aircraft, and find ways to use 3D printing to improve the performance and the reliability of the aircraft. And that's where, when Rob and I were talking, we decided, let's do one of these exhaust manifolds and reverse engineer it, print it, and actually run it on the aircraft.
Now, John, you mentioned 3D printing. Now, I understand that you chose 3D printing as the technology to fabricate these replacement parts for a reason.
That's right. Well, being with Concept Laser, we thought, what better way to apply this technology to an aircraft that's 70 years old. So that's where we really took a hard look, and we thought we'd find a way to reduce part count, because the original exhaust stack had a base, and then it had two forms, stainless steel sheet metal pieces, and then had a ring on the end. So you had 4 components and 34 inches of weld seam on that component. And we thought, well, this is ideal, right? Because you get stress fractures from the weld seams, and these do fatigue and wear over time. And we thought, we can print these in stainless steel, make it a duplicate, make it one part, and eliminate all those weld seams on the component. So that's what kind of drove us to do this particular part.
I'm with Ray Chu. He's principal at PADT Incorporated. And Ray, I understand scanning was the starting point for reverse engineering this 70-year-old part. Tell me about it.
So John sent me the existing welded sheet metal parts of this exhaust stack. And he said, Ray, I want to have a CAD data that I can put on in my 3D printer to print a replacement part. So we took the existing 4-piece welded assembly and used a blue light scanner, which has a very high resolution, will give us about 5 million data points per square inches. So we scan the whole assembly and take the point clouds data and turn into a meshed surface model, then smooth all the weld seams and all the machining surfaces, and recreate a 3-dimensional CAD data, and take that data, convert it into a 3D printed data format called STL. So I sent that data back to John, and they were able to put it in their machine and print this part.
John, Ray Chu at PADT just described how they scanned the part and actually created the STL file to make the part. But it's one thing to simulate it on a screen, it's another thing to actually build it. Now, tell me about the challenges of building this part.
Well, the first part you look at is the orientation, and you're trying to reduce the number of supports you're going to have, or if you do have supports, that's for some reason in the build. But in this instance, we built 2 at one time. We've oriented them like this, so we had supports on this down-facing surface here, and no supports going up vertically through the exhaust stack. So that turned out to work beautifully, because we're going to finish machine this base anyway, because that's what's going to mate to the aircraft. So these are the kinds of things you're thinking about when you're orienting a part, where these supports are going to be, what's easiest to remove them, what features are going to be hit with an EDM or perhaps machined. So those are some of the considerations. And these particular parts, we built 2 of these in 2 days.
Rob Connolly is the owner and pilot of Hurry Home Honey, this beautiful P-51D behind us. And Rob, the Packard Merlin engine that powers this aircraft, some 14,000 components if you include fasteners, there, a lot of wear items, and a high wear environment. This is a high performance aircraft. Now when it came time to source a replacement for the exhaust stack at this point, you chose 3D printing, and I understand that there's a reason for that.
Yes, well, it's certainly not a coincidence. 3D printing has been my career for the past almost 30 years, since the late 1980s. I was involved in the technology since it was invented. Back in the earliest days, the materials that we had available to us were just plastics, and not very high performance plastics at that. Fast forward to today, and companies such as Concept Laser Inc. and their ability to produce in metals and high performance metals like titanium or Inconel, or in the case of this exhaust stack, stainless steel, really opens up some new avenues to do things. They're really high performance parts.
Rob, in the early days of 3D printing, of course, there were concerns about densification. Are the parts fully dense? Are there inclusions? Are there voids? Those sorts of things in there. But the technology's advanced to the point now where working with the Concept Laser, you were fully confident that you could produce a flight-worthy part.
Right, well that issue is something that comes from the traditional manufacturing techniques of castings. Castings that traditionally had issues with inclusions, voids, and so forth, and it's something that you had to really inspect and perfect the process on. So that was something that everybody was concerned about with additive manufacturing and 3D printing when we started making these high-performance metal components. But we found out fairly early on that they did not suffer nearly as much from that problem as people suspected they might.
Now, John, the part you're holding now is clearly higher quality than the original 70-year-old component that's on the aircraft right now. Are we looking at a future in which 3D printed replacement parts are safer, stronger, better than the originals?
Absolutely. Certainly in the safer, stronger, better performance, part count reduction. There are just so many benefits to this technology. The elimination of 34 inches of weld seam, for example, that's a nice deal, right, from a labor standpoint and manufacturing and stress cracks and everything else. So it's definitely going to step up the game in every facet of whether it's aviation, medical, automotive. It's an exciting future.
John, how about the cost perspective? There's a perception that 3D printing is a very expensive way of making parts. Originally it was thought of as a prototyping technology exclusively. However, the cost of making a one-off stainless steel welded exhaust stack for an application like this by conventional fabricating techniques would be prohibitive, you'd think.
Be very expensive, very, very time consuming. You'd have to make the tooling, generate the sheet metal forms, weld the part, there's labor involved. So actually printing becomes so competitive, not only from cost, but this is an availability issue, right? There are only so many of these stacks left that were built in the 1940s, and that number diminishes and some components on this aircraft are outrageously expensive because there's such a limited supply. So I think that's where 3D printing can really make an impact, because you can generate these parts very quickly, reverse engineer them, print them, perhaps in better alloys, more durable alloys, and make a safer product in the end.
John, 50, 100 years from now, will be gone. This aircraft will likely still be flying. It'll be even more iconic than it is now. Now, can you see a future at that time when perhaps most of the component parts of this aircraft, maybe the whole aircraft itself, could be 3D printed?
It's certainly going to push that direction, right? We're just going to continually make steps forward to have this technology used more and more for that part count reduction, saving of weight, and increasing safety. That's what I think is one of the beautiful parts, is you're not giving anything up with this process. You're making parts that perform better, they're safer, and it's a fabulous future, whether it's in medical, aerospace, space, doesn't matter. This is touching every aspect of our lives. It's 3D printing.
70 years ago or 70 years in the future is 3D printing, according to John Murray.